All right, so today we are actually making a flip book. So this it's printed double-sided, and then this where it says back, you can imagine if you're working with some sort of notebook, you could glue or tape right here into your notebook, that section. And when you fold it over, this will actually be like the left hand side, the two left hand side tabs, and this over here will be like the right hand side. All right. So, a couple of things before we get started. Multiplication and division properties of radicals. You may have seen these before, but they're good to recall. So, for two numbers A and B, they're positive real numbers, right? Can't have any negatives going on under there. Then the square root of A times B is equal to the square root of A times the square root of B. And the square root of A divided by B is equal to the square root of A over the square root of B. And this can be really helpful for us when we are simplifying radicals, because a fully simplified radical is a radical expression where the radicand, or the thing under the radical, doesn't have any perfect square factors in it anymore. So if I can take a number and rewrite it as a perfect square times something else, then I can use these properties to help us simplify what's going on. So for your reference, I have put some common perfect squares here. We got 1 squared all the way through 15 squared. All right. So first, we're just going to look at things that are perfect squares, right? Squaring and square rooting are inverse operations, as you know, and so when we take the square root of, say, 81, we know 81 is just 9 squared, so those cancel and we're left with 9. All right, the square root of 196 is asking us what did we multiply by itself to get 196? And so the answer is 14. This one's a little bit trickier because I have this a coefficient of 3 out front. So whatever I get out of my radical will then be multiplied by this 3. So here I'm taking the square root of 121, which is 11. And so this is going to be 3 times that, or 33. All right, now you go ahead and try these try questions, and then we'll come back and go over them. All right, so square root of 144 is 12. The square root of 36 is 6, but it's getting multiplied by this negative 1/2. So my answer there is going to be negative 3. And here we're taking 4 times the square root of 16, which is 4. So we'll get out 16. All right. Now let's step it up a notch. I'm going to give you some radicands that aren't perfect squares, but they all contain perfect square factors. So be still on the lookout for these perfect squares. So first, I'm thinking, what is the largest perfect square that goes into 32? And so you might be thinking, well, 4 goes into 32, and you're absolutely right. But then I would still have another perfect square left over, and I'd have to simplify even further. So I always try to look for the largest perfect square. So the largest perfect square that's a factor of 32 is 16. So 16 times 2 is the same thing as radical 32. So this means I can take the square root of 16 and get 4, but poor 2 stays behind under the square root symbol because he's not a perfect square. All right, next let's look at the square root of 54. 54, I know I can write that as 9 times 6. And so when I take the square root of 9, I'll end up with 3 radical 6. And Next is 63, which is 9 times 7. So 7, of course, is prime, so it doesn't have a perfect square factors. So it stays under the radical. I'll have 3 radical 7. All right, go ahead and try these you-try problems here on the right. Pause the video, give it a shot, and then we'll chat. All right, so 108 here. 108 has perfect square factor at 36. It's 36 times 3. And so this will be 6 radical 3. In question B, we have this 2 out front, so it's going to have to stay there. And then 125 is 25 times 5. So when you take the square root of 25, and it comes out of the radical, right, I have to multiply 2 by 5. So I'll have 10 radical 5. Sometimes my students will ask about that stuff, so I think it's important to include from time to time. All right, and then 98. You might have been searching on that perfect square list for quite some time before you found the answer that worked. Maybe you even thought it was a trick question. But 49, a perfect square that divides evenly into 98. When I take the square root of that, I'll have 7, the square root of 2. All right. Now, some hot math gossip here, tea, I think we're calling it these days, is about rationalizing the denominator. So, as a good algebra teacher, I'm going to teach you how to rationalize the denominator, but I'll have you know there's plenty of mathematicians out there that think that this is, for lack of a better word, a useless skill. Anywho, mathematicians a while ago decided that a simplified is this rational expression. That should say radical expression. Oh dear. Anywho. Alright, so a radical expression cannot contain any radicals in the denominator. So to remedy this, we multiply by a form of 1 to change the look, but not the value of the expression. So this is like when we found common denominators with fractions. You could say multiply by 3 over 3, 5 over 5, and those wouldn't change the value of the fraction, but just how it looked, so that you could combine by addition or subtraction. So here I have 1 divided by radical 3. So what undoes radicals? Right, or square root is squaring. So what we can do is multiply this by itself, right? If I multiply by radical 3 over radical 3, I'm going to end up with radical 3 squared in the bottom. Or you can think about it as multiplying those radicants using the property we had above, and I'll have the square root of 9, which we know and love as 3. So I just have radical 3 over 3, which has the exact same value, right? This is equivalent to what we had at the beginning, but it looks better in the eyes of mathematicians. All right, so let's go ahead and do these 2 you-try problems. Alrighty, folks, so 2 over radical 2, if you multiply by radical 2 over itself, you would have gotten 2 radical 2 over 2, but of course those 2's there would cancel and we'd be left with just radical 2. And last but not least here, we've got 1 over radical 5, we'll multiply by radical 5 over itself, and end up with radical 5 over 5. And there you have it, everyone. Our cute little full book for simplified radicals.